So today we're going to look at some interesting aspects related to the hydrogen atom. The first thing I would like to kind of share with you is, we've already seen this in our previous lecture, and that is the plotting of the angular wave functions. I think we've already plotted a 1s orbital. We've plotted, this is another s orbital. We've also this, by the way, is a p orbital, a pz orbital, and by superpositions of two spherical harmonics we were able to plot two other kinds of p orbitals. We call them the px orbital and a py orbital. So the chemists would generally, just a quick recap on drawing orbitals. Just as an example, if I were to take the spherical harmonic function for which L equals 1 and ML equals 1, this function is primarily given over here. It's a complex function, so it's difficult to plot it. I would need to plot its real part and its imaginary part separately. So what I could do, I could take this function and add to it the function with ML equals -1. So I create a superposition of two wave functions. So I take one function with a positive sign and one function with the negative sign. So one of these functions, and then of course I need to normalize as well. So this is a normalized wave function, another normalized wave function. When I add the two, I need to normalize the superposition as well. So if I were to form this superposition 1 over under root 2, the first function given here is simply minus 3 over 8 pi square root sine theta E plus I phi, right? So this is this function over here, correct? And I add to this the second harmonic function. So when I add the second harmonic function, I get a positive sign, which is the sign below, plus 3 over 8 pi under root sine theta E minus I phi. All right. So this is a superposition of two wave functions. Each one of these wave functions is a solution to the Schrodinger equation. Just the angular part. Yes, please.
Sir, after the शुरू में minus क्यों लगाया?
Where?
1 over 100 के बाद bracket में जी.
Because for y equals L1 ML plus 1, I have a minus sign. So when I kind of add all of this together, I get 1 over under root 2, 3 over 8 pi. All of this I can take as common. Let's take the minus sign outside, and I'm left with a sine theta and E I phi minus E minus I phi, correct? So this of course is proportional to sine phi. This is 2 times iota times sine phi. So overall, the superposition of these wave functions becomes minus 2 iota over under root 2. I need to divide by 2, 3 over 8 pi. Sorry, I need to multiply with 2 because I want to put in a 2 in the denominator here. Sine theta sine phi. Correct? Yes, please.
So how did we get minus 2 iota over x squared?
Well, because e I theta minus e minus I theta over 2 is iota sine theta. So these are trigonometric identities. So this is my overall wave function. Now this is kind of purely imaginary. So it has a real part and an imaginary part. The real part is 0. So if I just plot the imaginary part of this wave function, and I can plot this in the form of a polar plot. So I have an x-axis, a y-axis, and a z-axis. So now what I'm going to plot is the imaginary part of this function. The imaginary part of this function is going to be proportional to sine theta sine phi. All of this is a constant. I really don't care about this constant for the time being, because I just want to plot the shape of the orbital. This is just controlling how big the orbital is. So if I were to plot sine theta sine phi on a 3-dimensional grid, what will it look like? This function is maximal when theta is 90 degrees. That's the xy plane. It's 0 when theta equals 0. So this function has a property that near the z-axis the function is 0, and as it proceeds towards the xy plane the amount of the orbital goes up, and it's also maximized when phi equals kind of 90 degrees. So the y-axis represents phi equals 90 degrees. So if I were to plot this orbital, it will be a lobe here and a lobe on the minus y-axis. This is what this orbital is going to look like, the imaginary part of this orbital. All right, and of course phi is positive whenever theta is between 0 and 90. Phi is positive, theta is positive, sine is positive. In this lower quadrant, theta between 90 and 180 degrees, sine theta is positive. Phi, however, takes up a positive value in this lobe and a negative value in this lobe, because on the y-axis here phi is 90 degrees and on the minus y-axis phi is 180 degrees. All right, so this is what this orbital looks like, and chemists like to call this orbital a py orbital because the lobes are kind of oriented on the y-axis. So this is a chemist's py orbital. Physicists' orbitals are just this thing and just this thing, but if you want to conform to the chemist's definitions of orbitals, you take the superpositions of the solutions of the Schrodinger equation and you get the chemist's p orbitals and d orbitals. Likewise, you can draw the pz orbital. We drew the pz orbital in the previous class. You can experiment drawing the px orbital. The px orbital will be obtained by putting a minus sign over here. Alright, so this is how the p orbitals come about. We still don't know precisely what the meaning of these wave functions are. These are just wave functions. Their modulus square, however, tells us about probability densities. We're going to figure that out today. Let's look at one more example of an orbital. Let's try drawing a d orbital. So if I were to focus my attention onto this orbital here, let's look at L equals 2, ML equals 0. Clearly, this is a d orbital because L equals 2. So far, I am not concerned with the radial part of the wave function. That's going to come later in our discussion. I'm just trying to draw orbitals, and these orbitals have some disposition, some orientation in three-dimensional space. They vary with theta and phi. So the R dependence comes later. Yes, please.
So why is it a d orbital?
Because that's how we define a d orbital.
So for A universal.
So L equals 0 is an s orbital, L equals 1 is a p orbital, L equals 2 is called a d orbital, L equals 3 is called an f orbital. Alright, so you have orbitals up till f. Now let's try plotting this orbital. So what we're trying to do is we're trying to plot wave functions. And how do I plot this? This is called a polar plot, by the way. A polar plot is drawn in the following fashion. The magnitude of a point on three-dimensional space is represented by how far are you from the origin. Alright. So at 90 degrees, you're further away from the origin, which means that the lobe is biggest at 90 degrees. That's where the value has its maximal. These are called polar plots. Yes, please.
Sir, on the second word, the first equation, वहाँ पे जो second two है वो कहाँ से आया?
Because of this definition, I think. Alright.
First two, क्योंकि दो ही नहीं है.
So this under 2, this comes from the superposition. When this is a normalized wave function and I add to this another normalized wave function, a new superposition is created. I want to add equal amounts of these two, so I put in a square root 2. Alright, so far so good. By the way, when I'm plotting these orbitals, this magnitude isn't really showing up anywhere. It's just the size of the orbital, and I don't care about this. I'm just plotting shapes. Orbital means shapes. Yes, please.
Theta is the angle between x and y.
Well, we've seen this. So theta is this angle. Okay. And phi is this angle. This is how we've defined our angles, the polar coordinates. Yes, please. सुपरपोजिशन से पहले
हमने सुपरपोजिशन ड्रॉ किया ना,
जी
तो अगर हम एक को ड्रॉ करते हैं
अगर हम if you just wanted to plot this, you just plot this, the real part of this will be sine theta cosine phi. I can plot it. The imaginary part will be sine theta sine phi. I can plot it in an analogous fashion. All right. Yes, please.
So why are there two 2's in the definition?
Why there are two?
Why? You have the two 2's in there. And
Where?
below this.
This one?
On the other. Over here after I you put another 2 over there.
The coefficient doesn't really matter, so I don't really care about on a blackboard. I don't really care about these things, but okay, you're Puritans, fine. Now let's plot this orbital. Okay, this is what I'm concerned with. So I'm going to plot y. L equals to, excuse me, this corresponds to a d orbital, and I'm plotting one of the ml's. So ml equals 0. ml could be plus minus 1, it could be plus minus 2 as well. I'm not plotting those orbitals, I'm just plotting this orbital. So the form for this orbital is 5 over 16 pi square root 3 cosine square theta minus 1. So this does not have any phi dependence. This orbital doesn't have a phi dependence. In fact, if I were to look at this table over here, ml equals 0, no phi dependence. ml equals 0, no phi dependence. ml equals 0, no phi dependence. So all the ml equals 0 orbitals are devoid of any phi dependence. What does that mean? Yes?
The orientation z and y axis.
So this really means that they don't depend upon z, they don't depend upon phi, sorry. which means, so if you go around the z axis, the orbital is symmetric. It's rotationally symmetric about the z axis, and it preserves a certain component of the angular momentum, as we will see. So if I were to plot this function, chemists are fond of plotting orbitals. So now what I'm trying to show to you is that the orbitals that you study when you study atomic structure and chemistry, basic chemistry, they are all making sense. They're all coming out from a quantum picture of the universe. So can you try plotting this wave function here? Forget about the coefficient doesn't matter. Can you plot 3 cosine squared theta minus 1 on a 3-dimensional grid? Make a polar plot. I give you 2 or 3 minutes to think about this, please. A very interesting shape is going to emerge. What I would do first is, first of all, I would like to make a graph between theta and 3 cosine squared theta minus 1 and see how this function changes with theta. That will enable you to draw the polar plot. अगर हाथ से काम नहीं करोगे कुछ नहीं होगा, देखने से फिजिक्स नहीं आती.
times multiply our cos square of minus 170. हम बस normal cos square लेना है.
-1 भी है, सही नहीं बनाया. -1 कहाँ गया? There's some -1 as well. Okay. So इसको 0. If this were the 0 axis, where would this graph go?
Above this.
Would it be between the x and y axes?
No.
Or between the y and z axis?
It should be symmetric about z because there's no phi dependence. बना के देखो. Any soul would like to share the results with me? Can you please? I can't really see. Come on. Try drawing better graphs. So first, so this can I see your notebook? I don't know why we've drawn many cosines. This looks more like it. Yeah, good. We've drawn many cosine square graphs. We've drawn many sine square graphs. So this is what it's going to look like. This is -1, 2, this is 0. So this point is negative here, negative here. What is this value of theta? Excuse me. This is pi by 2, 90 degrees. And where is the 0 crossing? What's this point? What's this point? 1 by cosine inverse of 1 over square root 3. This point is, this is about 57 degrees, I think. Cosine inverse 1 over square root 3. All right. So, by the way, this angle is called a magic angle in physics. Now, this is the variation of the distance from the origin versus theta in a polar plot. So what I would like to do now, I take my 3-dimensional grid. Let me finish now. When theta equals 0, my orbital has maximum value, which means I'm further away from the origin. So I mark a point over here. Then my distance from the origin keeps on decreasing as theta goes up. As theta goes up, I'm moving towards the equator, towards the xy plane in this 3-dimensional grid. Correct? When I approach about 57 degrees, my theta is 57 degrees. At that point, my orbital, its value goes to 0, which means I kind of jump onto the origin. So if I were to draw, this is my magic angle. This angle is 57 degrees. At this point, I will get back to the origin. And this also works if my, so if now my theta goes between 57 and 90 degrees, and my orbital then takes another finite value, albeit negative, but still it goes away from 0. It takes a negative value, reaches a minimum value, which means further away from the origin again, and at about 90 degrees it's this far from the origin. So I will get another lobe over here, a smaller lobe over here. In this region the orbital is positive, and in this region the orbital is negative. And when I move beyond 90 degrees, I once again approach this point. I'm still in the negative regime. I hit 0 again. There's a 0 crossing. So this goes back to 0 over here. Again, my orbital is negative here. And then I go beyond this point all the way up to 180 degrees. And I move further and further away from the origin, between all the way up to 180 degrees. So this is my 180 degree line. So my orbital grows bigger again with a positive value. And this has no dependence on phi. So if I just draw a section on the zy plane, I can just rotate it by 360 degrees about the z axis, and overall I will get a graph like this. Let me finish. So this is a graph of this orbital. Chemists like to call this orbital a d z square orbital. And if they were to plot this in 3 dimensions in a more realistic fashion, this is what they would normally draw. So this has a 3-dimensional kind of curvature, and then there's a donut shaped kind of ring centered around the equatorial plane. This is a z square orbital. It's just a plot of a wave function. Questions? There's a question here. Ali, sleep timer तो नहीं लगा हुआ इस पे? Any questions? Yes, please.
How are you analyzing the conceptual axis पे बना रहे हैं?
Sorry.
Orbital conceptual axis पे बना रहे हैं, ये कैसे पता लगा?
So this is z, x and y. So
Like the small one on the x-axis and the large one on the z-axis, how do you know that?
because this is much larger than this distance, all right? So the bigger lobe is between 0 and 90 degrees. All right?
सर
Yes, please.
आपने उस वाले को वहाँ से कैसे ट्रांसफर किया?
किस वाले को?
साइन वाला
So I think you should watch my or kind of discuss this with your colleagues. So I want to draw an orbital in 3 dimensions. How do I draw an orbital? I want to draw a polar plot. How do I draw a polar plot? I need to know how big is the orbital versus theta. How big is that orbital? The dependence is 3 cosine square theta minus 1. So this is determining how I build this thing. This functional dependence is determining how I build this. All right? Can you see? It's warming up. All right. Timer तो नहीं लगा हुआ इस पे? Any more questions about this? Anyone else? Yes, please.
मतलब था कि आपने शेप जो है उसकी वो बस ऐसे ही बनाते हैं हम वहाँ से अपने डायरेक्शन देखते
नहीं, from this graph, this is the graph of 3 cosine square theta minus 1. All right? Do you understand this graph? Now what I would like to do, I would like to draw what the orbital looks like in polar plot. This is a polar plot. So I start off at theta equals 0. That's the z-axis. I put a point on the z-axis. Where do I put a point? That is defined by the value of this function at theta equals 0, which is here. So I randomly put a point here. That shows the extremity of my orbital, the upper limit of my orbital, because the maximum value of this function is here. Then as my theta goes up, down, theta goes up, excuse me, my theta now goes up, which means I'm moving down. When I'm moving down, I take on points. So I consider this point, this is some theta. At this theta, I'm this much far away from the origin. So I identify that theta here and mark a point here. This point, this distance tells me the value of this function at this theta. And I keep on traversing or reflecting this graph onto this polar plot. That's how I draw it. Now what you could do as an exercise, so these are important questions I would like to ask you in an exam, for example. So let's take another example. You see this wave function? This corresponds to a d orbital. ML is plus 1, corresponding to the plus sign here. It's complex, I can't plot it. What I could do, I could take a superposition of the plus version and the minus version. And what kind of form do I get? Let's see. So I'm giving you one more example. I didn't intend to present another example, but for the sake of repetition, let's do this. So I take the superposition of the two states, the positive superposition of the two states, and I end up with sine theta. I'm just drawing the angular part, cosine theta. Once I get a positive exponent and once I get a negative exponent with a minus sign. So I get 2 iota sine phi. So this is a superposition that I create. If I take a negative superposition, I'll get a cosine phi over here. All right, is this clear? So I'm taking one kind of, no, not clear? So is this clear to you? So if I put a minus sign here, sorry, I put a positive sign here, I get something proportional to cosine theta. So once I can take a negative superposition, once I can take a positive superposition. In either of these cases, once I get a sine of the angle, and in the other case I get a cosine of the angle. All right. So I'm taking a superposition such that once I have a positive sign, once I have a negative sign. So I'm taking a positive superposition because the wave function has a native positive and a negative sign. So when I do that, I get a sine phi term. Now I want to plot this. All right. So let's try to plot this. I forget about the coefficients. So if I were to plot this, first of all, can I represent this as half sine of 2 theta sine of phi? Correct? Can you plot this? Make a polar plot that represents this orbital. X, Y, Z. Yes, please. Yes, please.
Why is the negative wave function at the y-axis?
Here? Because we are in this region. In this region, this function is negative. That's why. So between 57 degrees and 90 degrees and back to this point, this is the lobe that emerges and it has a negative value.
How does that emerge? Why does it go?
Well, you'll have to do a point by point kind of trajectory traversal. Try to plot this on a computer. That's what you would get. Try to plot this on Desmos or GeoGebra or something. This is what you would get. Can you try plotting this orbital, please? Anyone? Yes, please.
I wanted to ask कि जो हमारा इसका plot है, it is similar to that one, right?
This one? Not really. First of all, we're plotting another d orbital, another kind of d orbital. Come on, now you should try, you should do this. Theta is the angle from the z-axis and phi is the angle on the equatorial plane from the x-axis. Anyone? Anyone? I need one vote to proceed. Shabash. So phi is the phi dependence is sine phi. Where will I have the maximum orbital? At what value of phi? 90 degrees. So my orbital is kind of clustered around the y-axis, plus minus y-axis. Got it? So at 90 degrees and 270 degrees, my sine phi has big value in magnitude. Here it's going to be positive, on this side it's going to be negative. Now where is my this component maximum? At what value of theta is it maximum? At 45. So what this is very simple in fact. So at 45 degrees, theta equals 45 degrees on the zy plane, I get a lobe. I get a lobe here. I get a lobe here, and I get a lobe here. Flower shaped pattern, which is predominantly in the YZ plane. So if I were to look at this from the front, I look at this orbital from the front like this, YZ. X is coming out, X is pointing towards us. If I were to plot the wave, the orbital, it will have maximum kind of value centered around the theta equals 45 degrees axis, the theta equals 135 degrees axis. These lobes will be positive because sine phi is positive for phi equals 90 degrees. And when my phi becomes 270 degrees, sine phi becomes negative. So I will also have lobes towards this side, and they will be in the zy plane predominantly. They will extend out of the zy plane as well, but predominantly they will be in the zy plane, and the function will have a negative value over here. This is called, I think, a dzy orbital. There are 5 kinds of d orbitals because there are 5 kinds of mLs for d equals 2. So a dz square, a dxy, a dxz, and so on. So where phi equals 90 degrees, this is positive. Sine is also positive in this regime. All right, okay, I think you're correct. I think you're right because of this factor of 2 over here. Okay, thank you. This is what's going to look like. Because in this regime, theta is between 90 and 180 degrees. So sine 2 theta will be between 180 and 360, and it will take a negative value here. All right. So this is how we draw orbitals. And so far, we're not concerned with the R orbital. We're only concerned ourselves with what do these orbitals look like in an angular orientation. How do they look like in space? Now we have to come to the question of how far is the electron from the nucleus? Any questions about plotting orbitals? So I'm a 2-dimensional being, so is the blackboard. So this is actually extending in 3 dimensions. So this lobe is fat. It extends in other planes as well. All right. So but I can only draw it in 2 dimensions. So imagine this thing, even though I'm drawing it in 2 dimensions, but I'm rendering it in 3 dimensions. So you have to go around as well, okay? But it's predominantly in the YZ plane. Outside the YZ plane, so if I were to look at this from the top, let's look at this from the top. So this is now my x-axis, this is my y-axis. Now this lobe over here is above this plane, right? It's above this plane, correct? It's at 45 degrees, right? It's extending like this, okay, got it? But if I look at it from the top, this is what it's look like. So it's going towards the x-axis as well, okay? So but I can only draw, being a finite two-dimensional kind of human being, that's what I can draw. So you can visualize these orbitals. I've actually uploaded a link to three-dimensional visualization of orbitals on our website. Now let's come to the radial part. The second thing I would like to consider is the radial part of the wave function. I think I have to move on, otherwise if it's an urgent question. Yes, please.
सर पहले आपने d ऑर्बिटल में शेप निकाली थी वो एक कंप्लीट डम्बल बने हुए थे इसमें आप मतलब गैप्स क्यों हैं ये फायदे भी
This orbital is symmetric about the z-axis. This orbital here is not symmetric about the z-axis. It's symmetric about the x-axis. So different orbitals have different symmetries, all right, and that determines the angular momentum of the electron when it is inside this orbital. An s orbital is totally spherically symmetric. It does not have any angular dependence. Now I would like to talk a little bit about R's, the radial part of the wave function. The overall wave function is a product of the angular part and the radial part. So let's look at a few radial wave functions. Now here we have a listing of radial wave functions, right? So this is n equals 1, L equals 0, a 1s orbital. This is a 2s orbital, a 2p orbital, 3s orbital. So let me draw this orbital, a 1s orbital, a 2s orbital, and a 3s orbital, and plot it as a function of r. So first of all, let's draw a 1s orbital. I can actually easily do this on the blackboard because it's just an exponentially decaying function. So this is r, n equals 1, L equals 0. This is called a 1s orbital. This is chemist's notation. So if I were to plot this versus r, this is what I would get, right? Got it? And we have to figure out what does this mean. Does the orbital have a maximum value at the nucleus at r equals 0? We have to figure this out. So if I were to plot the 2s orbital, I can actually do this on the blackboard, but in order to convince you that what I'm drawing is the correct thing, let me plot this orbital and this orbital on the computer for you. So I choose a software of my choice. Okay. So I want to plot r to 0, so I kind of plot. I don't care about the coefficients. Just about r dependence. So I am plotting r to 0. So let me kind of increase the size a little bit further. So I plot minus r plus 2. I take my a naught to be equal to 1. So I'm plotting everything with respect to a naught. I'm plotting with respect to r over a naught. A naught is just a number. I can take that to be 1. I'm just looking at the form of this function into exponent of minus r over 2, correct? And I want to plot this with respect to r from 0 to some value, say 5 or 4. All right, so this should give me a 2s orbital. Let's plot this for up till a higher value of, this is what the 2s orbital looks like, minus r, right? So let me kind of plot range on. This is a 2s orbital. For your satisfaction, let me draw the 1s orbital as well. So a 1s orbital is simply exponent of minus r over 1, r, because a is 1. This is my 1s orbital, the one that I drew on the blackboard. Let me now draw a 3s orbital. For a 3s orbital, I look at the right. So I'm going to plot the top wave function. Plot. Now I have to be careful. First of all, I have a 3 over here, exponent minus r over 3. And what's my big factor? It's 2 over 9 into r square minus 2 into r plus 3. All of this is in parentheses. A I'm taking to be 1. So my horizontal axis is in units of A. It's actually r over a naught. So if I plot this, this is the 3s orbital, a very similar shape, but you notice there is another 0 crossing here, a 0 crossing here and a 0 crossing here. So these are just plots of the orbitals. On their own, they really don't tell you where the electron is. Because the next question I would like to ask is, looking at these wave functions in the r space, in the radial space, which are multiplied by the angular parts, can I answer the question, where is the electron? If I were to answer the question, where is the electron, given it's in say a 5s orbital or a 3d orbital, I'm just concerned with how far is the electron away from the nucleus. Looking at the wave functions is not alone sufficient. I need to find the probability density functions. I need to find where is the highest likelihood of locating the electron in terms of probabilities. So after a 10-minute break, I'm going to answer this question. So please be brisk in time, please reconvene in 10 minutes. So we plotted the orbital parts of the wave function. Excuse me, chiefs. We've plotted the orbital part, we've plotted the radial part of selected wave functions. Now the two have to be combined together in order to give you the overall wave function. And I need to answer the question, given the electron is in some orbital, where is the electron? We've seen when we discussed wave functions, this is not a legitimate question to ask. At best, we can associate a probability density function. So let's find out that probability density function. All right, so now we will move on to probability density functions. If I have a wave function in one dimension x, what is the probability density function? Wave function psi, which is just a function of x because I'm dealing with one dimensions only. What's the probability density function? Someone on the back? Probability density function is the modular square of this. Correct? Right?
Yes.
And if I multiply this with dx, a small distance x, what does this thing represent? Please, in simple English, clear language, can anyone raise one's hand to describe this in English? What does this expression mean? Yes, please.
The probability of, if this is a wave function of electron, the probability of finding electron in a slice width is dx.
At what point? At x. That's very important. So if I were, what does this mean? This means that if I had, this is my x and this is my psi of x modulus square, and I plot some wave function modulus squared, not the wave function, modulus square of the wave function, at some value of x, some value of x. I take a small section of length dx, then what I put in a box over there is the probability of locating that particle in an experiment in this region. Correct? This is the area under this graph in this region which is at x. So it's the region between x and x plus dx is the probability of locating the particle inside this region. A priori, before a measurement, the particle is kind of everywhere. The wave function describes where the particle is potentially to be found. In an experiment, the probability that it kind of fires in this small region is given by this. So this is a probability per unit length, called the probability density. In 3 dimensions, by the way, so this is I would like to ask questions of this kind. So if I have 2 points xa and xb, and I want to find the probability of locating this particle between these 2 limits, what would I do? I would integrate. I would integrate this object psi x mod square dx from x goes to xa to xb. Correct? That's what I would do. Now what is, if I have a 3-dimensional wave function like a 3D infinite well, which is cubic, spherical kind of arguments apply, but they're very unwieldy for a cube. For a cube you would like to deal with cubes. So for a 3-dimensional problem like in 3D infinite well, cubic shape, our wave function is 3-dimensional. Correct? Take the modulus square. What is this? This is a probability per unit volume. And what is, here I take a small region dx in 1D. What will be the corresponding small region in 3D? Right, it will be a small cube, a really small cube centered at x, y, z, and its volume is going to be dx, dy, dz. So this is a really small cube which I am exaggerating for clarity of dx, say dy, and say dz. So this is a region in space, and if I have a 3-dimensional wave function, this object here becomes my volume element. Correct? And if I were to find big probabilities, I take triple integrals with respect to x, with respect to y, and with respect to z. Got it? Now comes the hydrogen atom. In hydrogen atom, this form also holds. It holds. This does not depend upon your coordinate axis, but we have defined our wave function in terms of r, theta and phi. Why have we done that? Why haven't we chosen the x, y, z coordinate axes for a hydrogen atom? What's a physicist's answer to this question? My question is, why have we chosen the r, theta, phi coordinate representation instead of the x, y, z representation?
XYZ involves 3 variables, लेकिन R involves only 1 variable.
No, but we have theta and phi as well. The 3 variables are theta and phi, yes. Because of the potential energy, which is spherically symmetric, it depends upon r. And r is really x squared plus y squared plus z squared under root. So since our potential energy depends upon r, and it's independent of theta and phi, by the way, that's why the choice of r, theta and phi is more natural to the hydrogen atom. In fact, it's more natural to many atomic systems. So right now we do not have this form for the hydrogen atoms, electrons. We have this form, r, theta and phi. And we've noticed that this is really a product of r, which depends upon small r, and the spherical harmonic function, which depends upon theta and phi. And we had these quantum numbers n and l over here, and l and ml over here. So this wave function now has 3 quantum numbers, n, l and ml. In each one of these quantum numbers holds a special place. It quantizes something, as I will show later. Now, if I have the probability density, the naive answer would be that the probability density is now r, theta, phi, modulus square. But what I would really like to, I would first of all like to identify the volume element as well. So what is the counterpart to dx, dy, dz? What's the volume element that I write here? Volume of sphere? So the naive answer, innocent answer is dr, d theta, d phi. But what is this a volume of? Is this a volume of sphere? Small sphere? It's not, it's nothing, it's meaningless. This thing is meaningless. It doesn't have units of cubic meters. When you talk about 3 dimensions, you should have a volume element which has units cubic meters. In 1 dimension, you must have the corresponding volume element, which is the length element, units of meters. But here, this is really dimensionless. So we really want to come up with something which has more nicer units and which makes sense. So in 3D, we first of all have to define a volume element. 1D volume element is a length, small length. In 3D, it's a small cube. What is it in 3D in a spherical situation? Shell, but a shell is 2-dimensional. A small section of a shell, shabash, a small section of a shell is needed because the shell is complete. We need a small sliver of the shell, a small section of the shell. Now, if I were to kind of try to draw, I'm not a good artist, but let me try drawing something of this kind. So, So what I've done, I'm trying to draw a small section of a shell. So in 3D, so just imagine an orange, and you take a peel of the orange and you just draw a small rectangle or square on that peel. So that small section that remains, that small square on the peel, is my volume element, which has a certain radius. I mean, this is a length dr, right? A small length dr. Can you tell me what this length is going to be? This angle, by the way, is theta. This distance of this small element is r. So at r, I move further away from the origin by a small infinitesimal length dr. And can you guess what this curved length is going to be? Not d theta, r d theta, because an arc is r d theta. It's at radius r, but really the arc length is r d theta. So this length over here, which is roughly equal to this length over here, is between this length, this is r d theta. So now I have a three-dimensional element. I've identified two sides. One is dr, the other is r d theta. Now what I would like to do, I would like to identify kind of this length here, this length, or this length, or this length, or this length. How deep do I go back? Is this r d phi? Well, that's the first naive answer. But if I were to take this point towards the towards the z-axis, and I bring it back down to the equator, this point is expanding, this length is expanding, isn't it? So if I were to draw take this length, this pink length really depends upon the value of theta as well. So it's more than r d phi. What is it? It's not dr. It depends upon theta. It's r. So what is this length at theta equals 0? This just squeezes to 0. This length becomes 0. So let me draw a sphere. Suppose I draw this section here. This is a sphere. This angle is some angle d phi. This radius is r, and I am on the equatorial plane. What is this length equal to? R d phi. Good, shabash, very nice. Now for the same value of d phi, if I change my theta, which means this small opening now goes towards the north pole. So this is my small opening, my small angle d phi, and now if I want to have the same d phi and approach the north pole, this is how my, keeping d phi constant, how my hands will look like. They will shrink. So what is this length, what is this arc length on the surface of the sphere going to change to at theta equals 0? 0. In between, at some theta, I will have an intermediate value. So that is, can you think of a function that is maximal at 90 degrees and 0 at 0? Sine theta. So this length over here is r sine theta into d phi. Hence, this length is r sine theta d phi. Therefore, my volume element is r d theta into r sine theta. It's r sine square, r square sine theta dr d theta d phi. This is my volume element. Got it? So for 3 dimensions in the polar coordinates, my volume element is not dr d theta d phi. It's r squared sine theta d theta d phi. Now if I want to find overall, this is now the probability of locating the electron in a small volume located at the positions r, theta and phi, and the volume element is this much. All right, now let's look at a few examples. So if I were to kind of now try to simplify this a bit further, let's look at this element. My psi is a product of r and y. Correct? Now please pay attention. This is really crucial. This is the climax here. So my psi is r into y. This thing somewhere r into y. I take the modulus square of this. I get r is a function only of r, modulus square, y function of theta phi, modulus square, r square sine theta d theta dr d phi. Now what I would like to do now is, if I were to do any integration, I can separate out the r dependent parts and the theta phi dependent parts. Suppose I pose to you the question, how far is the electron likely to be found from the nucleus? Which means, how does the probability density look like as I change r, as I move further away from the nucleus? Right? And I really don't care about my theta and phi. So what I would like to do now is the following. I ask the question for what is the probability of locating the electron at r b, so all right, or between r and r plus dr. Okay, this is my question. How far is the electron from the nucleus? Not a good question, but how far can I find the electron in an experiment to be away from the nucleus by distance, at a distance r, within a small section dr? This is my question. So this question means that I'm only concerned about how far the electron is from the nucleus. I really don't care about the angles. So I can average over all the angles. Now this is a key moment of silence and a key moment of contemplation here, because what I would now like to do is, I take my psi, okay, my r square, capital R square. These are all the r dependent terms. And I take y, theta phi, modulus square, sine theta. and I have all my variables dr, d theta, d phi. So this is my probability of locating the electron in some small volume at distance r, theta, phi. Now I want to keep my r fixed. I just want to answer this question, which really means I want, no matter what the angular wave function is, I want to average out over all the values of theta possible, all the values of phi possible. Correct? How would I do that? First of all, I would need to construct a triple integral. All right. In fact, I just need a double integral because I want to average out the values of theta and phi. So on a sphere, so now I'm on a sphere. So this is my sphere, and I take a small shell on the sphere. This is my nucleus over here. This is my shell. This length, thickness of this shell is dr. Excuse me, please pay attention. Thickness of this shell is dr, and I want to find the probability of locating the electron inside the shell. A thin veneer of a shell, a thin slice of a shell of thickness dr. This is really three-dimensional, but I can't draw spheres on a blackboard, so this is kind of a three-dimensional shell, and I'm just plotting a section of it. Now if I want to find the probability of locating the electron in this shell, do I care about theta and phi? I really need to integrate over all possible values of theta, which means I need to go about in the circle, and all possible values of phi. So my answer is independent of theta and phi. My answer subsumes all theta and phi. I want to average out theta and phi. So here theta is 0, here theta is 90 degrees, here theta is 180 degrees, here phi is 90 degrees, and so I want to walk all over on the shell, keeping my distance r fixed, which means I take up all values of theta and phi. So if there is an insect living on this shell, and the insect is asked to go at every point on this shell, what the insect is going to do is that it's going to keep its r fixed and traverse all values of theta and phi. Correct? That's what a shell means. So what needs to be done here is I want to have all values of theta and phi possible as I go out on this shell. So if I want to traverse all the points on this shell, what are my ranges? What is my range for the variable theta, phi? Let's talk about phi first. Phi goes from 0 to 2 pi, okay? Got it? So I go all around in the circle once. What about my theta? Theta starts from 0, and where does my theta end? Where does it end? Speak up, don't be afraid. Pi, 180 degrees. I don't need to go all the way to 360 degrees because my phi takes care of that. So my theta goes from 0 to pi. All right? Yes,
What
please.
if we switch 2 pi into pi? Would that work?
No, that's not going to work. All right, so as far as the r dependent terms is concerned, they don't depend upon theta and phi. So I can write this as r square capital R modulus square dr, and the integral d phi goes from 0 to 2 pi. integral d theta. Theta goes from 0 to pi, and I have sine theta and a y, which depends upon theta and phi. Now I need to calculate first of all of this. Correct? Now the moment of truth is, and the kind of neat answer is, just give me a second. Let's pull up the spherical harmonic functions. These are all the spherical harmonic functions, at least the lower order ones. They are higher order ones. They're infinite spherical functions. Now the integral, of course, seemingly depends upon, by the way, this is modular square, seemingly depends upon what the value of y is. All right? Now it really turns out that this answer is independent of the y that you take. It's really independent of the y that you take. You pick up any kind of y, and see, and let's see what. So let's pick up the first kind of y and calculate what I've written in this yellow box. Okay? So I'm just doing the integral for the yellow box. So I need d phi. Phi goes from 0 to 2 pi. D theta. Theta goes from 0 to pi. Sine theta. And my first function is 1 over under root 4 pi, which is a constant. I just pick one particular kind of the spherical harmonic function, the lowest order one. And then I can pick up others as well, one by one. So if I were to do this, so 1 over 4 pi, so this doesn't have any theta in it, so it just has a phi. So what's the value of this integral? 2 pi. What's the value of this integral? Chalo, 1 over 4 pi ka square, sorry. Thank you. So what is this integral equal to? What is the integral of sine theta? Minus cosine theta. With these limits, what does it become? Come on. 2 plus 2. Right? So this is 2. The answer is 1. All right? If I were to take the second kind, so let's take the second kind. So 3 over 4 pi, it doesn't have any phi dependence, so still I get 2 pi from here, and I have 0 to pi d theta sine theta and the square of that, which is cosine square theta. So I will still get 1. All right. So the integral of this will be, I think, cosine cube over 3 with the minus sign. Put the limits, I get, I think, 2 over 3, and the answer is 1. No matter what y I choose, this result, no matter what the value of L is, no matter what the value of ml is, this result is always equal to 1. Got it? This is always equal to 1. What this means is that all of these spherical harmonic functions, their modulus square integrated over the surface of a sphere of any radius, the answer is 1, which is really showing that these spherical harmonic functions are normalized. All right, so far so good. Any questions? I give you 2 or 3 minutes to think about this. Let's take questions. Yes, please.
Why did we take pi over the theta integral?
Sorry?
Why did we take pi for the theta integral? Why not 2 pi?
So the first question that our friend has asked is, why is this upper limit in theta equal to pi? That's your question, not why is it 2 pi? Because that 2 pi is, what does theta between pi and 2 pi mean? So this is theta equals 0, excuse me, theta equals 0, theta goes up, so let's go like this, theta goes up, this is the x-axis, theta 90 degrees, theta is now 180 degrees. Now if I want to go to the back side of this kind of sphere, I don't need to do that because my phi is already taking care of that. Otherwise, I'll do double counting. All right. So my theta between 0 and pi and my phi between 0 and 2 pi takes me to all the points on the sphere. Any more questions? Yes, please.
Then why can't we reverse cap?
I think you should think about this. I don't think you can reverse this.
No, why not आप theta को 2 pi तक लेके जाएं और
मेरा नहीं ख्याल ऐसे होगा क्योंकि जब at the north and the south pole your phi becomes undefined. There is no concept of phi at, so the answer lies in differential geometry. I don't think I know the answer at the top of my head at the moment, but I don't think you can do that. Yes, please. There was a question here from a woman. Question? Now what's turning out to be the case is that if I look at this integral, all of this equals 1. So now let's look at what's left behind. What's left behind is, if I were, no, doesn't this look like a one-dimensional problem? No murmurs, please. This is really important. This is looking like a one-dimensional problem with a dx here, a dr here, one variable r, and all of this capital R modulus square but with a small r square is now a probability density in one dimensions. So it's not just r capital R square, but it's capital R square multiplied by this variable squared r square that is telling us the probability density per unit length along the radius of this atom. So at one shell, in one shell, the probability of locating the electron is going to be dr, which is the thickness of this shell, multiplied by the radial wave function modulus squared multiplied with small r squared. So not just r modulus square, you really need to multiply this with small r square as well to find out the radial probability density. And I'm going to plot this now. So, but first of all, on the blackboard, let me write what we've seen so far. The radial probability density which is not just r squared, it's actually small r squared multiplied by this capital R squared. And if you want to find the probability of locating the electron in a shell, I need to multiply this radial probability density with the length of that thickness of that shell, which is dr. So let's try to plot this. Now what I'm going to do is I'm going to take the radial wave functions Where are my glasses? So these are the radial wave functions. All right. I need to take the modulus square of these. I need to multiply each one of them with small r square and plot it and see what it looks like. So let's first consider the 1s orbital. Okay. So I define this as the 1s wave function, exponent minus r. Right? So this is exponent minus r. I forget about the size of it because I'm only concerned with the shape of this function. I'm not really concerned with the size of this. I can integrate all of these functions modulus square into r square from 0 to infinity. I'll get 1. Okay, but let's forget about that for a minute. So this is my 1s orbital. So I want to plot this, but I want to plot the modulus square of this multiplied with small r square. So I take 1s and I square it. It's a real function, so I can easily square it. And I multiply this with r square. And I plot this. And I plot, say, from r from 0 to 5 or 3. Let's give it, I think it's not recognizing, let's call it 1s. 1s. This is what this function looks like. This is the radial probability density, which tells us where is the highest likelihood of finding the electron when it's inside the 1s orbital of a hydrogen atom. And where is this object peaking? It's peaking at 1, which is a0, which is the Bohr radius. And it's 0 at the nucleus, as it should be. Answers the question that we raised in the previous lecture. There's no likelihood of finding the electron at the nucleus, in complete conformity to the Heisenberg uncertainty principle. And the maximum likelihood is at the Bohr radius, at r equals a0 here. In fact, you can take this function modulus square into r square and find out its maxima and minima. It will have a maximum at r equals a0. This is, so the electron could be found anywhere if it's in the 1s orbital, which is the ground state for the hydrogen atom. The electron could really be found anywhere a priori. But when you do a measurement, the highest likelihood is that you locate this at the Bohr radius, which was present, and this idea was presented by Bohr before wave functions were invented. So it conforms with the old quantum theory. Let's see what happens with the 2s orbital. So what do you expect in the 2s orbital, by the way? What should the radial probability density for a 2s orbital look like? Where should this radial probability density be the highest? Let's see if it's at 2 times the Bohr radius. Let's see. So I think this is my 2s orbital. Let's call this 2s. This is my 2s orbital, okay, which is simply this term over here, r20. I forget about the big constants. I'm not concerned about them. Tawajjo. So what I would do now is I would kind of modulus square this. It's real, So I can simply take the square. Otherwise, I'll have to do a modulus square. It's real, so I'm okay. So I take the square of this. I multiply this with r square, which is the radial probability density. I get this. I can take the derivative of this, equate it to 0 to find out the turning points, the maxima and the minima of this function. But I can also plot it. So if I were to plot this, I plot it. R goes, say, from 0 to 4 times more. Let's do this all the way up till 8. This is what I get. It's not 2 times the Bohr radius, it's something else. So this is the radial probability density for a 2s orbital. At some value, which is I think roughly about 5 times the Bohr radius, you will have the maximum likelihood of locating this electron. And if I were to plot this in 3 dimensions, let's first of all plot this radial probability density in 3 dimensions. Remember that the 1s orbital doesn't have any theta and phi dependence, so we are safe. I don't have to go through the labor of plotting these wave functions as a function of angle, because there is no angular dependence for any s orbital. So if I were to plot this radial probability density for a 1s orbital modulus square, that's what I'm going to plot. The plot is there in front of you, but if I were to draw a cloud of electrons, a cloud diagram of an electron at some a naught, this is what it's going to look like. It's going to have its maximum density at a naught. Likewise, for a 2s orbital, it's going to have a second maximum over here. We're done. Some density in between. This is generally called a K shell. This is called an L shell. N equals 1, N equals 2, N equals 3, and so on. See you on Tuesday.